Hello, Professor. So we cannot hear you.
Hello. Yeah. Okay. Okay. So I hope now they're hearing. If they're still complaining, please let me know. Okay. Maybe not. Oh, there's a comment here. Oh. Okay. Yeah. Or was it not in progress? Okay. Okay, so I was just trying to kind of not really, I don't want to spend time on recapping decision trees, and that's why I wanted to quickly summarize what we saw. A construction approach, there's a lot of variations in pruning, a lot of variations in choosing how to make a split, even if you choose a feature itself, like you choose a feature, given a feature, how do you split, especially if it's numerical, or if it has multiple values as a categorical variable. So there are a lot of choices, okay, and that was just for one single decision tree. We will look at other variations, extensions later on, and then we'll further talk about diagnosing these models. The biggest takeaway from this class is not really the model construction, a specific model, but actually like overall, we'll kind of see a pattern in types of questions we ask for each model. For example, with KNNs and decision trees, we really didn't spend too much time on how do we say a model is the best, okay, and that kind of becomes apparent for the kind of parametric models we'll see today, which is a linear model. And there we have to explicitly say how are you going to say something is better than another candidate model, okay. So these are the types of questions that you want to kind of carry over. The exact specific construction of the tree you can and you will actually be working on it in the assignment, but you'll see variations elsewhere, okay? And so that should ideally not be the point of confusion, okay. Okay, let's come back to the decision tree. What is this playing music? Okay, I'll choose to ignore it for now. And okay, so let's come back to this illustration example. I slightly changed the output. Now this output is actually two classes, pass and fail. Okay, so fail is red and pass is blue. Again, similar type of features. Let's say it's just homework and exams as the two features, so two-dimensional data, very similar to the type of data sets you're going to work with in assignment 1. Here's an example decision tree, right? So it's just it's splitting on one of the features, homework, and it's a numeric feature. So you wanna pick a threshold or a split point, and here it says ideally the way you should represent what we saw last time was write the feature name here, and then left hand side would be the feature name greater than or less than something, and the right hand side would be feature name greater than something. Okay, but you'll see variations like this. So let's say it's feature name greater than 90 goes to the left, okay, and then again feature name greater than 74 goes to the left, okay, and so this is an example construction. Now, if you want to visualize it, because it's two-dimensional, this is how you visualize it. You have one of the features exams and the other feature homework on the y and x axis, and then you're seeing a bunch of red dots corresponding to let's say the fail class, and the blue dots corresponding to the pass class, and you can see the first level split, right? The first level split is at 90, and so from there, if you're on the if you're less than 90, then there's a different split. If you're greater than 90, there's a different split. Okay, so if you really extend this procedure, and especially for numeric features, you can actually revisit the split point again and again. So you can, the feature that you want to split again and again. For example, once you're split on exam feature, then again you can pick up and split on the homework feature. Okay, so you can see here, this is not exactly, it's just synthetic data, but you can see how many lot of splitting has happened, right? So so this is one, I guess, artifact of using decision trees. So if you could have a very messy decision boundary. Okay, so the colored area is actually just if you pick a test point there, which class does it belong to, either pass or fail, and so the decision boundary is characterized by these boundary points here. Okay, so the region points. Okay, and why do they look exactly horizontal and vertical? Is exactly because the splits are like that. Okay, splits are exactly according to the feature being greater or less than some threshold value, and that's why the boundaries are either include vertical lines or horizontal lines. So instead of that, I mean, this is just a motivation to say that, hey, maybe there's a simpler explanation for this mapping from input space to output space. The simpler mapping is, for example, could be this, right? So the two features, you take the values, they are numeric features, and add them up. And if they cross a certain threshold, you will say it's one class, and if it's not crossing a certain threshold, it's another class. In this case, the decision boundary is going to be a line in if the input space is a two-dimensional plane, okay, and if the input space is three-dimensional space, then the decision boundary is going to look like a plane, and so decision boundary is just going to be one dimension less than the space input dimension, the size of the input space or dimensionality of the input space. Okay. Now, so you can see that this is a nice condition. But our targets were two classes, right? So pass or fail. So what we'll see is actually we'll kind of go one step and talk about an adjacent problem, which is when our output is actually numeric. Okay? So the adjacent problem where our output is numeric is when you add up exam plus homework. This is numeric. This is numeric. So exam plus homework will also be numeric, for example, right? So and I'm going to relate that adjacent problem where the output is numeric to this class problem in a second, and it's going to be very basic, but at the same time, the same idea can be used whenever you want to move from a regression problem to a classification problem. Okay? So regression can be used for classification, and this is just a teaser to show you that here there's only classification happening in this picture, but we'll come back and kind of relate this to regression not behind the scenes, but related to this. So here's the adjacent problem. I've added one more feature here, which is attendance/participation, and then here's the output variable. Okay, output variable now is numeric, and so what we're going to do is, given these three features and this output value and this table, Excel sheet or CSV or whatever you want to call it, or even from a query from a SQL database. So from there, what we want to create is again that mapping, right? So remember from first lecture, we just want to always create, at least for this class of problems, supervised learning problems, we always want to create that black box, the function match map from input space to output space. So what we're going to do with this linear model setting is going to hypothesize or represent how this function looks like. Okay, so this candidate function that we want to build looks like. I mean, that has to approximate ideally the underlying function, if there is one. But what is our restriction? That the function should look like this. So h subscript is represented by this Greek letter theta, which represents the parameters of this model, and x is as usual the input. So this function h of x is represented in this way. Okay, so it's just a element-wise multiplication plus element-wise multiplication and a summation going on. So element-wise multiplication just means, hey, x homework, x exam, and x attendance / participation. Those are three attributes or three features, and they take potentially three different values. Let's say 82, 80, and 85. Element-wise multiplication just means if you think of the vector, it's a three-dimensional vector. X is a three-dimensional vector, right? Here, this x is actually just a short form to represent the three-dimensional vector. So you just multiply element-wise, as in first coordinate times another one number, second coordinate times another number, third coordinate times another number, theta 1, theta 2, theta 3. Okay, and then you add them up. Okay, and there's also another number which is theta naught, also present in this definition, function definition. So you just do element-wise multiplication, add them up inside your function definition. Okay, and then return whatever the right-hand side evaluates to. Okay, so this theta parameter, which is the Greek letter, is also a vector. Okay, so that vector you can think of as four-dimensional vector, theta naught, theta 1, theta 2, theta 3, or you can think of three-dimensional. We'll see that it's not an ambiguity here. It's just how just your choice. Okay, how you wanna call it. So in particular, what we'll write is h theta in the short form as this. Okay, I mean, we have seen sigma notation before and looking at KNN model, right? So it's just summing over I is equal to 1 to little n. Little n, remember, is the dimensionality of our input space. Okay, so in the previous illustration it was three columns, and so n is equal to 3. Little n is equal to 3, and so we're going to write it this way. So I is equal to 0 to n of theta I times xi. So element-wise multiplication at every coordinate, and then sum over all the coordinates. Okay. Now, where did theta naught go? We can see that we are summing over I is equal to 0 to n. So there's actually 4 terms here if little n is 3, and x naught, is not defined in the previous slide definition. So we'll just say x naught is equal to 1, by default. Okay. So with that, we get a shorter form. So this is a linear function. Okay. So I think I asked folks to recall, or at least quickly check what I wanted you guys to look at linear algebra basics, right? Prereq. So you should know why it's called a linear function. Linear functions satisfy some certain properties, and matrices represent linear functions as well. Okay. So what properties does a linear function satisfy? Does anybody have a ready answer? I mean, it satisfies, let's say, a couple of properties or more than one. So any one property that you want to kind of say? Max power. Or if you think of polynomial, the degree of the polynomial is 1. Yeah, sure, that is fine. But in general, so why is what's the special about why the word linear? I guess the question.
Because it has a straight line.
So here, if theta was theta square, you're saying this is not a linear function?
I'm not sure about the theta not, but the theta one is square, then it should not be, because the impact of x, then it will be, it won't have a linear impact on x naught.
Okay, so I guess there is an ambiguity. I think let me say linear with respect to something. Okay, so this h is linear with respect to its input. Okay, it's also linear with respect to theta. Because you can see the degree of x's. If you think of this as a function of x, is max degree is not greater than 1, strictly greater than 1. And it's also a function of theta. It's also linear in theta. But let's not worry about function of theta. Okay, let's focus on x's. X's powers are not x square or x cube or something. So it's linear in x. Okay, so let's not worry about. So theta are parameters. The function is a function of x, and x is taken as linear input. So that's it. Yeah.
Theta can have square, or can have more than power any one.
Yeah, they can have, right? So I mean, so if you think of theta as power something, you can just replace that with some other value. Yeah, some other notation if you want. So this is a good question in the sense that it is a little bit of a trap, because I didn't say explicitly, I guess, earlier. Let's think of linear function of something. Here the function I'm kind of focusing on is function of its input, which is x. Okay. It's also linear in theta. Okay. So you can think of x as parameter and theta as input if you want, but let's keep it simple. Theta is something internal to the function, and it's taking an x as an input and it's linearly transforming it. Okay. So think of linear transformation, right? Think of a matrix. It's a linear transformation. Takes a vector as an input, produces another vector as an output. Right? Here, h theta is also a linear transformation, linear function. It's taking a vector as an input and producing a vector as an output, but the vector is just 1 cross 1. Okay, it's just producing one number. Okay, so it's taking a vector and producing one number, but in general, you could take a vector and produce another vector, and that's you do it by a matrix, right? So a matrix is a linear transformation. Similarly, this function is also linear transformation, and you can see the vector notation in maybe this slide or next slide as well. I'll explain that again. So what are the parameters? Theta. Theta 1 to n are called the weight parameters, and these are the parameters that we, for example, we will care to regularize. I don't know if some of you might have seen ridge regression before. So we only care about theta 1 to n, although there's theta naught as well. Theta naught we ideally will not regularize, but theta naught has a couple of other names. It's called bias or the intercept as well. Okay, so people have seen simple regression, right? This should kind of should be a review, because theta naught is that intercept and theta 1 is the slope, if you think of simple regression. Okay, and multiple linear regression also, this is exactly multiple linear regression. So you have little n number of features or inputs, and theta naught is still the bias of the intercept term. Okay. Okay, so because we kind of folded in and said, hey, let's assume there's a fictitious x naught, an extra feature, like a degenerate feature, or it's not called degenerate, but extra feature. Let's call it. It always takes a value x. It always takes a value 1 for every data point. Okay, that lets us simplify the notation, because otherwise we'll have to always write an extra plus theta naught. Now you can just write it this way, right? So this summation, element-wise multiplication summation, is just what is called an inner product. Okay, so this is a shorthand notation that you should be familiar with. Okay, this is called an inner product. It's exactly defined at the first line. Okay, so theta transpose x is nothing but element-wise multiply theta with x and then sum it over. Okay, so this should be now familiar to you in the sense of it's in a matrix notation. So think of this theta transpose. Now theta is a vector, right? It's a vector with n plus 1 coordinates, right? It's a column vector, okay, with n plus 1 coordinates. You take a transpose, so now it's a row vector, or basically you can also think of it as a matrix with only one row and n plus 1 columns. Okay, now you have a matrix, and you're multiplying a vector from the right hand side. Matrix times a vector should be ideally another vector, but here it's just a degenerate number. I mean, or you can think of it as a vector also, but it's 1 cross 1, so it's just one number. Okay, so instead of theta transpose, let's say there was a huge matrix, some other matrix. Okay, then that matrix would create a vector as well. So I'm just trying to say that this inner product is nothing very different from a linear transformation that you might have reviewed in linear algebra prereq, right? Any questions or confusion here? I mean, the objective of this class is to really disambiguate these gaps. Okay, it's not so much about that you don't know linear models. You actually probably already, all of you know linear models from several classes from before. But it's just a good exercise to talk more formally, a little bit more formally, of what these models are, what are they, how do you define it, how do you explain the model, and so on. Okay. Yeah.
Why is bias so important? Because in all the class of models, parametric models, so right from linear to neural, we do add a bias.
Yes.
Why is that so important?
So, well, I mean, think of simple regression, right? So, simple regression case where you are regressing, let's say, income versus education level, and let's say both are numeric, right? Now, if you don't have this bias, you are forcing the linear relationship to go through 0. So when education level is, let's say, 0 units, whatever that means, you need to have income 0, which may not be the case, right? So even if education level is 0 units, income could be, whatever, $10 or whatever, $100,000. I don't know, but you are restricting your function class. Like you're searching for, you're imposing more constraints if you don't add a bias. And that bias or this extra term, technically, if for those who are super interested in the exact definition, the extra term here actually makes this function an affine function. Okay, not exactly a linear function. It's an affine function, but that technical detail is not important for at the first level for us. But bias is just needed to get around the case that I just mentioned. Okay, that's true even for the simple regression case. Now imagine for multiple regression or even nonlinear functions, this bias term doesn't appear in such several models. Okay, it only appears in certain types of models like this linear model and some neural networks and so on. This just for representing a richer relationship between input and output. Okay, so if you say, hey, I don't want to use bias, which essentially means that I want to set theta not to be 0. You're saying I want to use a smaller function space within which I'm going to search for the relationship between input space and output space. So it's just a question of where you want to search for that approximating function or the hypothesis function, right? The fit function. Any other questions? Okay, so as I said, I just want to briefly mention the goal for at least the first part is to talk about something called loss function, which again many of you may be familiar with. We're going to talk about loss function. We're going to talk about how to optimize, which is gradient descent methods. So those are the things that are coming up. Just to give you a sense of why we are spending so much time on linear models. The model class itself is kind of straightforward, but kind of we want to ground this notion of a loss, and therefore generalize from that misclassification loss that we saw before. Okay, we saw misclassification loss as a criteria to split in decision trees. But that's not its only purpose. We can use it for scoring any model. So there's generalizability. Okay, so given again, this is just a notational recap. You have the data set represented by capital D. Elements are the entries, the rows of that data set, represented by x superscript I, y superscript I, and let's say this boldface R represents the real line. Okay, and real line to the power n just means you're multiplying these real lines. Okay, this input space is being represented by R to the power n. It just means that each coordinate or each attribute is at least for this slide is numeric, and it's taking a value on the real line. So the first coordinate is taking a value on the real line, second coordinate is taking a value on the real line, and so on. And so it's just a shorthand notation. And this E type of a notation just means belongs to. Okay, I think I might have mentioned it a couple of times before, but if it is not clear, please ask. Okay, so we want to just be super clear. And these are just shorthand notation. Instead of writing it this way, you can always use English to say, hey, we have n data points, and each point is numeric, and it takes a value from 0 to 1 or whatever, minus infinity to infinity. You can write it that way. Okay. So there's no one particular way to write all these things, these type of statements. Okay, so for given a data set D, we want to figure out how to get the parameters theta. Okay, so that's the equation. Similar to the KNN case or in the decision tree case, we wanted something at the end of the day, a function which can, given any new points, say what the class is or what the numeric score is. Similarly here, to be able to say what for any new point what the output is, you want to say what theta is, right? So that's why we want to pick theta, and hopefully it's best in some sense. And how do we say something is best? Somebody has to give us a score, give us some signal for, hey, I chose some theta vector, what's the score? I mean, what's the performance, right? And some other theta vector, what's the performance? Maybe one is better than the other, maybe both have the same performance. All such questions have to be answered. And one metric, one very natural way to say what is better is that, hey, if you give me a theta, I can say what h theta of xi is, and hopefully that is close to yi in my training data. Okay, So that means that theta is probably good. Okay. And that's what we're going to do in the next few slides. So how to define this a little bit more formally, so that we can do computation on it. In particular, we are going to do gradient descent on it as an approach. And what properties does it need to satisfy? Okay, we'll see what properties just mean what are the nice things that it should have so that it actually qualifies as a way to quantify the performance of a model with values theta, one values of theta or another set of values of theta. So here's one candidate. Okay, so here we're using the term cost function or loss function. Okay, we've already seen misclassification loss before. That's slightly different. Here you can see that we are actually in the regression case. Okay, so we are actually thinking of output as in fact in the previous slide we wrote output belonging to this set. Okay, the set of reals has too many numbers. Okay, you can't count them. Think of the classification problem, which has a finite set, right? So class 1 versus class 2, pass versus fail, or grade A versus B versus C. So the set is the output space is finite. Here it's infinite. So here's an example of a loss function. So again, let's pass this. So we are representing the loss function by this letter capital J. Okay, we're going to reuse it, and that's why I want to kind of mention the notation here. J is a function of theta. Okay, it's also a function of the data set. I could write theta comma that's D object, but I don't want to explicitly write it for now. So it's a function which is a sum of little m number of terms. Okay, there's one term per data point in my training data. Okay, so if my training data has 100 observations, 100 rows, then I have 100 terms in this that define this j theta function. Okay, it's a function of theta. Why do I want it a function of theta? First of all, is because if I plug in different theta vectors, I should get a kind of a score, some sort of score or performance number, which says one theta vector is better than the other theta vector. Okay, and you can see the function, for each example, each data point is nothing but h theta of xi minus yi the whole square. Okay, it's just a square of the difference between what the function at the given theta value predicts versus what the truth is in the training data. Okay, so that's the function, and in the next few slides we're going to talk about why is this a good starting choice. I mean, this is not the only choice, right? You can have 100 different ways to say how your prediction is different from the true value in the training data. For example, why should there be a square here, right? You can always say, hey, why not the absolute difference between those two? That's also a valid thing to do. Why should there be a 1/2 here? Okay, there's no need for a 1/2. Okay, that seems like a very minor point. No need for a 1/2. Why not? Why just square? Why not to the power 4, to the power 3, or something else? Okay, so some choices are not good. Like to the power 3 may not be a good idea, but to the power 4 is still a valid thing to say. Okay, so but let's start with one candidate and then talk about why some other candidates may work, may not work, how to work with them. Okay, so we'll talk about some properties of this guy maybe a few slides from now, but let's say this is a choice, and it seems natural in the sense that it's not sensitive. I want to say one property right here is that it's not sensitive to the values of the signs of the predictions and the truth. Okay, so whether the truth is -10 units and the prediction is -9 units, or whether your prediction is 9 units and the truth is 10 units, the difference is still it's invariant to the sign. Okay, so that's why there's a square there. If it was not the case, then you would have some issues first of all, but absolute value also takes care of that issue. Okay, but let's say this is a candidate scoring choice. Okay, so or a way to quantify the performance of a model of a theta vector. Now what we want to do is, if this is how I'm going to score, this doesn't tell me how to find the best theta. We're going to spend a few minutes to discuss how to get the best theta if this is the way we are going to score. Okay, so one thing you can do is like keep generating some thetas and say, hey, what's the score, what's the score, what's the score, and keep track of the best one, right? You can do that. but there's some interesting technique. One interesting technique is what we'll look at. Yes.
I have a doubt here. So I'm trying to understand this particular part. So where the xi,
Yeah.
is it a vector?
Yes, it's a vector.
So basically every single time when I'm running this particular part from I equal to 1 to m, so every single time I'm using a particular vector. And
Using each of the little m vectors. So if I have 100 data points, so here now what we want to find is the best theta. Data set is fixed. Okay, 100. So data set is fixed means the features are also fixed, right? The xi and y are fixed. Fixed in the sense that so where is this? So this data set, which is this collection of xi y pairs, is fixed. Okay, it's the training data or the data that we have. What we want to find is the best theta. So for any theta, what's the scoring? What is the way to say whether it's a good theta or not? Is like this. So plug in a theta. I'm going to use that data set to say, hey, what is the score for that theta? Right. So 2 units. Maybe some other theta has a score of 3 units. Some other theta has a score of 10 units. Okay. So since I'm mapping, so what this function is doing is given a theta vector. Given a theta vector, it's producing one number. Okay, it's a function. So that loss bracket input theta produces return some number. Right. That's what this computation is. So hopefully that number being high or low means the theta is good or not.
This is on the condition of a fixed data set, and
Yeah.
this is running a row-wise computation. So if I take the first row of my data set,
let me actually, I don't think there is no file here, right? So all I'm saying is this is f j, right, of theta comma d ideally, but d is the data set, right? So I'm just saying, so here you want to say, so here you want to say use a data set point to compute that summation. Given the input. Use the data set these points to compute the summation given the theta. So that summation is exactly this, right? So given, if I tell you the data set xi yi pair, where x is a vector, y is a scalar, xi is that n-dimensional vector. Okay, so you can first compute, differences like this, right? So given the theta, I can tell you what h theta of xi is. That's a linear transformation, right? I can compute that extra column h theta of each training data. Now I have 2 columns. Now I only focus on 2 columns. This h theta derived column and the yi column. And just to take the difference. Okay, that's another column. Then take the square of that element column and then sum them up. And multiply by 1/2, and then that's it. That's what you return. Right. So that's what you written here. So writing this function is easy. Right. I hope return that summation. Right, so this should be fine. I mean, you should be able to implement this given the data set and theta. Right. I mean, I'm using a programming perspective because ultimately, you don't want to stick just with concepts, right? You want to write them. These are tangible objects, tangible things, functions, function definitions, objects, whatever they are. There seem to be some questions. No. Yeah.
Does the loss function need to satisfy some condition or property to be defined as a loss function? One of them is obviously it should be derivable if we have to use it for this.
It should be differentiable.
It should be differentiable, sorry.
Yeah.
Apart from other properties that
so misclassification loss, for example, is not differentiable. Okay. But still, it doesn't have to be differentiable. If it can be differentiated, then it's it's good property to have. So I think more fundamental to that is, does it reflect our intuition? Okay. So for example, for some theta, maybe this value is super small. Okay. does that mean that theta is good? Like for example, there may be a theta for which is exactly 0, j theta is 0, which means that I'm not suffering loss. I'm able to exactly predict everything on my training data outputs. Okay, maybe then that means the scoring function is maybe good. But for example, here you can already see that it's not negative. For example, it's not going to be less than 0 ever. Otherwise, the other properties we'll see actually. So differentiability is one which we'll rely on for the next algorithm, but algorithm material. So by the way, algorithm just means again a procedure. Okay, so whenever we use the word algorithm, loosely we just mean a stepwise procedure where we say step 1 do something, step 2 do something, like a for loop, essentially. Typically for loop, but it can be anything. Anything that you define a sequence of steps in Python is essentially an algorithm. So what we've done so far is define the model and define the criteria by which we can say some model is good or not. Okay, given the model, by which I just mean the theta vector, I can say give a score, right? Whether that score is high or low kind of corresponds to whether the model is good or not. Okay, so I just gave you 2 ingredients. Now we need to use them together to kind of find the best model. That's the missing part still, to find the best model. Okay? We just gave the model spec, right? We didn't specify what the theta exactly is. We just said, hey, what you need to find thetas because the model definition looks like this, which has these thetas as coefficient, or the things that you need to element wise multiply and add. Okay, so we just gave the model spec on the loss function definition. In the loss function is actually not very specific to linear model, so you can actually use the same loss function for anything else, any other model that you may come across, including deep learning models later on. Okay, so this is not specific to linear models yet. Okay. Okay, so the learning algorithm or the learning procedure to find the best model, as I said, the goal is to choose the best parameter that minimizes the cost or that loss function. Okay, which as the property basically it's natural choice because it's trying to find the theta which lets the function imitate the data set the most. Imitate doesn't like mimic the y values in the data set the most. So here's a approach. Okay, so the approach is to use what's called gradient descent. Okay, and we'll talk about gradient descent in the next slide. But pictorially, what's happening? So let's think of a let's say theta is just 2-dimensional. Okay, although here we're writing as x comma y in these axes, but just think of that as I only have to find like theta naught and theta 1. Let's say okay, just 2 dimensions, 2 parameters, 2 coordinates, 2 unknown numbers to search for. Okay. Then it may happen, and we'll see when it can happen, that the cost function for any value of theta may look like this. Okay, so in the sense that for theta 0, 0, let's say 2 coordinates 0, 0, it has some value. Okay, it doesn't have to be this red star, it's some other number, let's say. And for some minus 2 and 0, maybe it's some other number, and so on. So if you actually evaluate at every point, let's say discrete point, let's say you discretize that space, 2-dimensional space, because we are searching on the 2-dimensional space, right, of theta 1 comma theta naught, let's say. If you discretize that, maybe the loss function looks like this. This is an illustration. We'll come back to say whether the loss function actually looks like this or not. If the loss function looks like this, and we can only plot this because we are saying the input is two-dimensional, so the third dimension is being used to represent the loss. Okay, third coordinate is just a loss. The z coordinate is just the loss value. If it looks like this, then there's an algorithm called gradient descent, okay, which is an iterative procedure which makes you go from any point on this loss function, any point in the sense that any starting value of theta, okay, it lets you iteratively make some steps and go to the bottom of this loss function. Why do you want to go to the bottom? Because you want to minimize the loss. Okay, so there's a learning procedure which can let you do that. Okay, so this is just a teaser for that you can get to the bottom of a loss function. Okay, and this loss function, by the way, is called convex loss function. It's just a word. It represents, so some types of functions are convex, some types of functions are not convex. Okay, many functions have different properties, right? Like just the loss, for example, loss function has some properties that it is not negative. Right? Similarly, this function that is represented here in this illustration, it's called a convex function. Okay? Convex functions look like balls, like a parabola, inverted parabola, or like a bowl, where there is only one bottom essentially. Okay, so this looks like a single valley if you want to think about it that way. So you have to get to the bottom of the valley, and gradient descent, for example, lets you, is one way to get to the bottom of that valley. Okay, so that's why it's called a convex function, because it has a single like a valley. There are many, and so you can imagine there are other functions which doesn't have a single valley. Maybe it has more than one valleys or bottom region, and so those are called non-convex functions. Okay, so here's an illustration for that. Even if so, here's a function which is some, again, theta1, theta2. Here I guess it's written better. So 2 dimensions, two parameters to be searched for, and red means high values, blue means low values. Okay, we are not able to, I mean, if you plot this in, let's say, Python or MATLAB or whichever, you can probably sometimes scroll and see how the loss function looks like. But here it has different regions. Okay, so for example, there are hills and valleys. So there's some valley or low values here. There's some hill-like region here, and then again there's some low value here, right? So it's not exactly like a bowl. Okay, that's called a non-convex function. That's all. We'll not look at mathematical details at this point about these, but you can formally write them as when the function is not convex and when it is a convex function. But even in this case, whether the function is convex or not, you can always use this gradient procedure, this one particular procedure we're going to look at next, to be able to get to some reasonable value, some reasonable model. Okay, some reasonable model. Yeah, I mean, in this illustration, we're just showing that, okay, maybe if you started from there, and maybe because of the way you kind of did this iterative procedure that we're going to talk about in a second, you might come to this valley, or maybe because of, you started from a slightly different point, you could go to a different valley. Okay, that could happen because our learning algorithm, so machine learning or learning algorithm here is to learn the best theta. That's I mean, you can also, alternatively use a less, you can also use a different word like finding the best theta. So it's just a search procedure. You already specified the model specification, which is that it has to be something like a theta vector. You already told me what the criteria is. So it's just a searching for the best theta that minimizes that loss function. Okay, just a search procedure. Okay, so I kind of wanted to show those two illustrations before talking about the approach. The approach is called gradient descent. Okay, as I said, it's gradient descent purpose is to, at the end of its computational procedure, that algorithm, you're going to get a candidate theta. Okay, so some output, some theta will be given to you. You can also get the objective value, or so you can also get the loss or cost corresponding to that theta. Okay, but ultimately we want the theta because we want to use that theta as a best theta that we could get from the training data. Okay. So how do we do this gradient descent? How does this algorithm look like? Okay, this procedure look like? You start from a randomly chosen starting point. Okay. What is the starting point? The starting point is exactly some theta value. Okay, some value for that vector theta. So let's say you start with vector theta, which is all 0. That's also some starting point. Or you start with a vector theta, which is you call numpy.random.random. Okay, so it will fill up some random numbers. Okay, that's also some random initialization. Okay, and you first create that starting theta, and then what we do is keep making some baby steps towards that towards the gradient direction. Okay, and we'll talk about gradient quite a bit in the next few slides. So let's we'll spend some time on it. So we want to make a gradient step towards the gradient direction or the negative of the gradient direction. We'll talk about gradient in a second. And then so it's an iterative procedure, and so what we start from some random point, make a gradient step, and then repeat this whole repeat this gradient steps, making these gradient steps again and again and again. So you don't restart or reinitialize again and again, but you start from an initialization point, and then you keep making these gradient steps, okay, until the parameters converge. Okay, and we'll talk about what is meant by parameter converging in a second. Yeah, so that's the template. So you start from some random point and you kind of do this kind of black box gradient step, and we'll talk about gradient step now. Okay. So repeat until the parameter converged just means that the parameter, like if I take one more gradient step, the parameter is not changing much. Okay, so maybe I landed at some theta values 2, 3, 4, 1. Let's say that's it's a four numbers, 4 coordinates, 3-dimensional let's say regression problem. So I got to 2, 3, 4, 1. Now from there, if I take a gradient step, I still get 2, 3, 4, 1. Okay, maybe it can happen. And so there it's like if I take even 100 gradient steps, I'll still have the same 2, 3, 4, 1. Then I'm not making any progress. So it's like I've converged somewhere. Okay. Here in the bracket it says, the slide is saying it's stuck in the local minima. It's just again a technical word for us. It's just we'll just think about it conceptually. Local minima just means you could have come to this valley. In that valley, maybe you're not making changes even though you take gradient steps. Okay, so that's also convergence. Okay. But ideally, if it's a nice situation, then you get to the bottom and there you've converged in the sense that you're not changing the parameter values, but you're also not in a local minimum. Okay, so in convex loss functions, there is a minimum. Okay, there's a bottom, but since there's only one value, there's only one bottom. So it's like a global minimum. Okay. So the word global and local, they have some connotations even in programming, but here it just means global means it doesn't matter. It doesn't matter where you start from, initialize from. There's only one minima to get to. Okay, that's a global minima. And here this function has like multiple minima because there's a valley here, there's a valley here, and so you could end up here, and so those are local minima. I mean, if the scope of the function is just this, then maybe this is the global minima, but you may not get to it. Okay, so what is that gradient step? So here is an example. So here is an example definition of this first bullet point. Okay, keep making a step towards the gradient direction. Okay, that is saying, hey, I have a theta vector. I need to kind of iterate on them. Let's focus on one coordinate first. Let's focus on one coordinate. I mean, for all the other coordinates, you can also write the same equation. It's going to be the same. So in coordinate j, okay, so let's say theta is 4-dimensional again, the running example from our illustration. So theta j means theta naught, theta 1, theta 2, theta 3. Okay, so for each theta, we'll say the step is going to be whatever the current theta value is, because we initialize, we'll have always a current theta value. That theta value, you subtract a small quantity. Okay, so that quantity is the partial derivative of the loss with respect to that theta j parameter. Okay, so what we're doing is coordinate wise, we're just saying, hey, you always, so we're going to evaluate the right hand side. Okay, to evaluate the right hand side, we need to have all the inputs, all the values present to evaluate the right hand side. So what are the values that we need to evaluate the right hand side? One is theta j itself, and we do have it because the starting point is we always have a randomly initialized theta. So of course, if it's an initialized theta, theta j will always be available, right? To even making a step, and even after you compute the step, there's going to be a new theta. So there's always going to be theta j present to evaluate the right hand side. We also need the second quantity. There's some Greek letter alpha. Just think of it as some fixed number, just like 0.01 for example. For now, okay, it's just a fixed number for now. Okay, it's called a learning rate, but for now, just think of alpha as a fixed number. So this is fixed number. Theta j is available. Now the only missing thing is this partial derivative of j theta. Okay, so j theta, remember, it's a function of theta. Okay, given a theta, it's producing a single number. Now I'm asking, what is the partial derivative of j theta with respect to theta j? It just means, hey, can you tell me how much does j theta change its output when I keep everything else the same, but only slightly change theta j? Okay, like this. So when I slightly change theta j, keeping everything else, which affects the function, which is basically all other coordinates of theta, fixed, then how much does the output change? Okay. So that rate of change is this gradient. Okay, this partial derivative. So the word gradient of a function, by the way, the gradient of a function with respect to its input, theta here, theta, let's say again, think of it as a 4-dimensional vector. the gradient of the loss with respect to its input, which is a 4-dimensional vector, is going to be a 4-dimensional vector. Okay, so gradient is a 4-dimensional vector. Each coordinate of the gradient is just a partial derivative of that function with respect to theta 1 or theta naught, theta 1, theta 2, theta 3. So gradient is just a thing of a vector where each coordinate, the jth coordinate is just this. Okay, the jth coordinate is just this, and it's just one number. Okay, it's just asking how much does the output change when I change that coordinate, keeping everything else the same. Any questions here? Yeah. Yeah. So all I'm saying is, let's say, so theta is, let's say, I don't know, right? So let me just use T1, okay? T1, T2, T3, and there is also theta naught. Okay. So I'm not writing full theta, but here T's mean just theta 1, 0, 1, 2, and 3. So so this function here, given a theta, produces one number as an output, right? So now the gradient of j, right, with respect to theta is going to be again some vector. Okay, so the vector is just going to be the partial of j, j with respect to theta t0 and so on. So the remaining will be the same. Can just write it. I don't know if that works. No. Control Z. Right. So this is the gradient of j with respect to theta. So since theta is 4-dimensional, gradient is a vector which is 4-dimensional. So it's in the same space as theta. So if you think of theta in the 4-dimensional vector space, gradient is also a vector it's a vector in that vector space. Okay. And it's just each coordinate is just a, how much does j change when I change that one coordinate, that part of the input, keeping everything else the same. Okay. So generally what you do is evaluate the gradient at a given value of theta. Okay. So let's maybe look at this. Is this the right? Yeah. You can't see the mouse. Okay. Oh, okay, there is a small box which is not letting me. Okay, we'll just use this. Okay. Right. So let's come back to this figure, or even this figure. So j is a function of 2-dimensional theta, right? So the gradient is going to be a vector which is 2-dimensional. So that's kind of clear, right? So I just wrote it from, if you 2-dimensional input to that function and the function produces one number, then the gradient of that function with respect to the two inputs is just going to be a 2-dimensional vector, which is gradient. Each coordinate is just a partial derivative of that function with respect to that coordinate, theta naught or theta 1, for example. And what I wanted to say was that that gradient depends on where you're evaluating it. Okay, which means that the gradient of this function j theta 1 depends on whether I'm evaluating the gradient at, let's say, what is this, 0.7 comma 0.4, or whether I'm evaluating it at 0.1 comma 0.8. So depending on where I want to find the gradient may be different. Okay, unless the function is, let's say something like flat, or the function is like a plane, then it doesn't matter where you're evaluating gradients. If it's a plane, it has the same slope. Gradient is like a slope in one dimension. But I wanted to talk about the vector space version in general. So we'll spend some more time, so it will be more clearer. But that's what a gradient is, and this is just a partial derivative, an element of the gradient. Okay. Yeah. Yeah. How do we compute this? We will see how to compute this for the cost function that we chose in the next few slides. So we will find how to compute this. In that graph, so let me see if there's a picture. Nope. So okay, this one doesn't matter. So let's actually pick this one. So let's ignore the second cross in a plus sign here. That's not important. So let's say your random initialization is first plus. Okay. So this is some value, let's say 0.9 and 0.2. Let's say some starting point theta naught and theta 1. You started there, and at that point you're computing the gradient. Okay, that's some two-dimensional vector. The gradient is gonna be, you can think of the gradient. You can't imagine the gradient on the loss surface. Okay, the point of the gradient is the gradient lies in the input space. Okay, so you should really visualize the gradient as, hey, in this 2D plane, at that point, wherever that point is, how does that vector look like? The gradient vector. It will have two numbers, so it will have a direction, right, in 2D. So you can visualize. I mean, you can visualize things only on the loss surface, but they're misleading. Okay? What you want to look at is on the 2D plane, which is theta naught comma theta 1 plane. This square here, there was a starting point, and the gradient of the loss kind of gives you a small arrow in some direction, and that arrow direction happens to be apparently this direction. So that small baby step is going to give you a new point, which is here. Okay. I think we don't have visualization here, unfortunately, and Notepad is not good enough to show that visualization. But we'll talk about a little bit more when we work with the square law, and then hopefully it will become a little bit more clear. Yeah, you should think of gradient as lying is a small vector in this 2D plane. Okay, this theta naught comma theta 1 plane. Okay, and all this, what is happening is you're just taking the first part of the gradient and subtracting it from the first part of your existing point. So let's say get the new first part of your next point, and similarly theta 1. Similarly, you're taking the second coordinate of the gradient and subtracting it from the second coordinate of the original point to get the new second coordinate. So if there were if theta naught theta 1 in the previous example, there will be two such equations. Okay. So if you vectorize that equation, there will be a vector here. There will be a vector here, which is the gradient, and this is going to be the original point, which is a two-dimensional vector, and your output point is also a two-dimensional vector. Yeah.
So you initialize the theta value.
Yeah. So let me write that. Yeah. So step 0 is get an initial theta. So maybe some 4 numbers there. NumPy.random. That's it.
You have a range. If you're doing NumPy.random, so it will randomly generate 4 values.
From 0 to 1. If you use NumPy.random, you'll get something between 0 to 1 each one. But you don't have to do that, right? I mean, here we are just assuming you can get any number if you want.
There's no range. You can any number.
I mean, it depends on the problem that you're solving. Here in the linear model specification, we didn't say, hey, thetas have to be exactly between 0 to 1 or 0 to 2 or anything like that. Since we did not say that, the starting initial point could be anything. So if you prefer theta to be exactly between, they have to be finally between 0 to 1, your initialization can also say, hey, I only want to initialize a point between 0 to 1. You can say that. But then the problem is that version of restricting your thetas or your iterates to be within that region is a slightly different algorithm. Okay? So it's not.
The loss function is different or theta. So
yes.
Theta should be correct in order to get you less loss. So
theta should be correct.
Meaning, I mean, we discussed that it should be an ideal value because based upon theta only the loss function is being determined. Right?
For any theta, the function will give you some number. So if the theta is bad, the function hopefully gives you a bad number, like a really large number.
So you don't know whether this is a good value or a bad value for theta unless until you
Evaluate it with J, yeah.
So even for initializing, so we will have to, we will not give a range, so we don't know which is the ideal range in order to get a next loss function.
Yes, we don't know. We don't know. Yeah. So when you say initialize, we don't know which one is actually going to give you a decent number.
Exactly. How do you initialize? So you don't know which is going to give you the next loss.
So it can give me a high loss. That's fine. Initial point can give me a very high loss. It's okay. As long as it's not infinity or something, it's okay. No, we don't have to track that number. Oh, if you have restrictions on theta, you know that, hey, I want to have theta naught between 0 to 1, theta 1 also between 0 to 1, and so on, then that's a slightly different problem. There's a slightly different search problem. It's a restricted search problem. Here, the search problem is not restricted. Here, we just say, hey, I don't know what the theta is. I only can tell you what the cost function is, which is determined by my training data. So whatever theta you can figure out, try to figure out, I will not impose further restrictions on theta. Whatever theta just means that my original restriction, okay, I guess the confusion is, what is the restriction on theta? Thetas are just reals, okay, real valued. I didn't write it anywhere. Okay, I didn't write it, but yeah, sorry, I should have written it here. But thetas are just, each one is a real valued number. Okay, in the sense that there is no restriction at this point. But if you have a preference that thetas have to be exactly between 0 to 1, then that's a slightly different problem. Okay, and I don't think we should consider that, because let's consider the simplest problem first, which is this, and then let's talk about if there's restriction, what we do. Okay, and by starting point, we can start anywhere. Okay, so if the starting point happens to give like a loss of 1,000 units, 100,000 units, that's fine. Okay, because gradient descent will actually still get you to a good point eventually.
That's why I want to know that algorithm will give you, irrespective of whatever the loss function is, it will give you the best one.
It will give you a best one, yes, it will, but sometimes it may not. Okay, but here for at least our linear case, it will give us a good one, at least. So what have we fixed, right? We have already mentioned the function specification is this theta transpose x, or whatever this summation here, and we have also assumed that our loss we want to work with for now is this. Given these two, it doesn't matter where you start, you will actually get to the good one, as long as this caveat is just that as long as this alpha is not too bad, like take alpha to be like 0.01 or something, and you'll be fine. Yeah. Yes, there's a question. Yeah. So that's what we're doing, right? So it doesn't matter whether we are not going to explicitly track. So let's think of a more simpler strategy, right? Forget about gradient descent. We'll start with some initial theta. It seems to have a high loss value. We'll slightly change it, maybe change some coordinates, and again evaluate the loss function, see whether it's going up or down. You can linearly like try to create another candidate and keep evaluating what the loss function is, and maybe you'll get to a good theta candidate. Okay, but how do you go to the next one? It's not clear, right? If you just try to look at this loss or the loss value for every theta, it's unclear how to go from, let's say you're at a bad one, how do you not, next one that you pick, how do you not pick another bad one? Like you want to kind of avoid that, right? So that you can avoid by taking information into account, which is that gradient information, which is that information about the loss function. It's still the information about loss function, but it says that, hey, loss function looks like a ball, so the gradient can make you go down the ball, and so the next point will be kind of, most likely that you will definitely reduce the loss. Okay? Whereas if you just track the original loss only and forget about gradient, then it's unclear how to go to the next point. I don't know if that answered your question. I mean, at this point we are very abstract, and so I don't know if how the people have kind of still confused. But we will kind of specialize this to the loss that we have. Okay, we have a particular parameter. The way it interacts with the loss is given to us because h theta is defined, and then j theta is also defined, and so we'll look at how the gradient looks like. Okay. Yeah. Okay, we will get to overfitting soon, but they could overfit, yes. Even linear models, so it's all relative. Okay, linear models are some of the more simpler models, but they could also overfit on the data. It can happen. you cannot outright reject that, hey, we have not overfit on the data. Yeah, we will get to overfitting later. Okay, right now we just want to find the theta using training data, and then we can talk about, hey, what is the actual performance and can it generalize or not. Just like we had to do pruning and stuff on the decision tree, there may be some extra things we need to do here. Okay. See what is the time? Okay, let's take a 7-minute break. And resume at resume in 7 minutes, okay? And if you have questions about this, I mean not the next slide, but just up to this point, then please come forward and we can briefly discuss. Okay, let's actually resume. Yeah, sorry about the shorter break, but we were in that flow of trying to understand gradient design, so let's try to do that. If needed, I'll switch out the document camera, but for now, let's see how the understanding is. So what we want to say at this for this slide is just a kind of a high-level concept of what's going on. We want to start with a randomly initialized point, theta, some theta starting point, starting vector. When you say point, think of that as a vector, and then we want to kind of do a for loop. Okay, for loop where we do coordinate wise. Coordinate just means if theta is 4-dimensional, then each of the 4 coordinates we want to make updates. Okay, in the for loop. So every step of the for loop, the old theta values are changed to some new theta values, and that's how there's an update going on. You can do this update for, if you want to run a for loop, you can run it for 100 iterations, 1000 iterations, or you can switch out to a while loop where you say, hey, as long as the new theta and old theta values are not too different, you can continue doing that gradient update, or this step 1. Okay. So that's the high-level template, and we'll specialize that to our loss function, which is the squared loss function that you saw in a couple of slides ago, so that things are becoming more clearer. Just a couple of comments is that if the cost function is convex, which is so this is a convex loss function. We'll not define convex. What is meant by convex formally? It's not needed at this point. If the loss function is convex, there's only one value. So whatever as long as you can get to the bottom, that is the a good solution. Okay, that's a global optima or global minima. Like if you're minimizing this loss function. Okay, optima or minima is just a word that people use to say, hey, you get to some good value in the input, in the search space. Okay, input search space theta 1, theta 2. Here it's not labeled correctly, but theta 1, theta 2. If it's not convex, you'll get to a potentially potentially some minima. It may be global or it may be local, but there is no guarantee. Okay? So like something like this. And so one trick to get around this is maybe you can start with multiple initializations. So maybe you can run this whole procedure, this sequence of steps, a couple of times with maybe 10 times with different starting points. Okay, maybe one of the starting points will get to a different value. Maybe all of them get to a different value. Maybe if all of them get the same value, maybe it's not good. But if they get to different values, maybe one of the values is deeper than the other, and so you get a better, lower loss, lower cost. Let's actually now starting about the gradient. As I said, gradient is a vector, and each point of the gradient is a partial derivative of the function with respect to one input coordinate, right? So let's focus on let's what we're trying to do now is drop complexity, and so let's say we only have one training data, one data point in our training data. Okay, so that's just, let's say x comma y is the only data point in our training data. Okay, so we don't have these 100 data points, 100 observations. The table, the data set is only like one row, okay, for simplicity. So what is the partial derivative of this loss. Okay, loss is defined 2 slides ago. We had a sum over all the data points. The sum just vanishes. Everything else remains the same. So since the sum vanishes, the only terms remaining is 1/2 times the square of h theta of x minus y, where x and y are, let's say, fixed. We're not indexing it by superscript 1 for simplicity, but think of x and y are not, not to be touched, in the sense they're fixed numbers. The x is a vector which is fixed, and y is some number which is fixed. Okay. I don't know if I. Okay, so we have this j theta, and we want to find the partial derivative with respect to theta j. Okay, because once we compute this, then this is exactly what's going to go into the theta j's equation, the update equation. If you can find it for theta I, then the same thing will go into the theta i's update equation. Okay, this partial derivative, by the way, should be a single number, and that may depend on some current value of the theta vector. Okay, maybe, for example, it can depend on the current value of theta j itself. Okay. For simplicity, I don't know if I can switch to the document camera. Try. No. So let's say, let's take a simple example first. Y is equal to, oh my god, it's not visible. So let's take y is equal to 1/2 x squared. Okay, so we have this, right? So what is the gradient of y, the partial derivative of y with respect to x, right? It's very, so many of you may have it. One of you can you answer? What is it? Why are you guys so unconfident? Like, be confident. You can't see this? Oh wow, I can see it. It's document camera in use. Okay, just one more button to send it to the projectors. Actually, oh, we can do both. Okay, so yeah, sorry. So this was the function, and you can easily answer what's the gradient of y with respect to the partial derivative of y with respect to x. Okay, it's just x, right? So this partial derivative of y with respect to x is also the gradient of y with respect to x, because it's one dimensional. So if there were, let's say it was 1/2 x squared plus 1/2 maybe z squared, then y is a function of two inputs, x and z, then you would write like the gradient would be partial derivative of y with respect to x, and maybe another term which would be partial derivative with respect to z, and then you combine them together one below the other, and that would be the gradient vector. Okay. So my point with this example is that the partial derivative can depend on the input. So the partial derivative of x, y with respect to x, depends on what the current value of x is. It's not a constant. Okay. And sometimes it may not just depend on x. Maybe it may depend on z also. It could happen. Okay, if the z was also another part of the y, this definition. Okay. So just wanted to make that point. And so let's come back to our slide, which I don't know what the issue is. Oh yeah, they can see the document camera. Yeah, so we take the partial derivative. This is exactly the same function. Instead of h theta x minus y, you can just call it some z, intermediate z. So 1/2 of z squared is just 1/2 times 2 times z. and then the partial derivative with respect to z itself, which again, you know, is by definition this, right? So this step should be kind of clear, right? So what we did is take the derivative with respect to this complex function, and then what remains is the derivative with respect to the inside, the argument of that squared function. That's this. This is, by the way, calculus prereq refresher. If you have time, please have a look at it again. Okay, for those people, it's not good, but we will change it in a second. And also, I think for the remote audience, we need to come back, or maybe not. I think I'm sharing. Yeah. So I'll just share. Okay, so partial derivative with respect to this function here. Now it's just there is no squares and, you know, extra coefficients going on. What is this function? This function is exactly this inside. H theta of x is exactly that, you know, element-wise product plus the summation, right? So that's the definition of that function h at any given theta. Now this is a function, the one inside the large bracket is just a function of theta. There are n terms. Each term, so there are n plus 1 plus one more term. Okay, so n plus 2 terms. Each, you know, there's only one term which is kind of depends on theta j, and all of the other ones are not dependent on theta j. Okay, right? In this summation here, there are n plus 2 terms, right? 0 to n, which is n plus 1 term, plus one more term, which is n plus 2 terms. All those terms, there's only one term which involves theta j. Everything else is like not a function of theta j. So if I change theta j, they don't vary. Okay, they are the same, fixed. So they all kind of vanish. So the only term that remains is theta j xj, because that varies with theta j. And so partial derivative of theta j xj with respect to theta j is just xj, and that's what we got here. Okay. So any confusion on this slide? So we just wanted to work out at least one example of, hey, that was a loss function, which is a squared loss function. If you only focus on one example, then the gradient of the loss with respect to one coordinate of theta j, is nothing but this. Okay. And now you can kind of, in hindsight, justify, hey, why are we passing along this 1/2? Is because we wanted to cancel 1/2 with 2. Okay, and there was no other purpose. Otherwise, we could have just not have this 1/2 and we would have an extra 2 in the front. Okay, there's, you know, that's one minor comment. Now we did this for only one training example. Now imagine if there were all the little m training examples, all the 100 training examples. What would happen? Right? What would happen is there would be a summation over m that will still be that will be there at the output. Okay, because every term will look like this. Okay, so the partial derivative of a function, which is the sum of 100 terms, is like the partial derivative of the first term plus the partial derivative of the second term plus the partial derivative of the third term, and so on. By each term you'll get an expression like this. Okay, and so the summation will still be the same. I mean, it still will remain. Okay, nothing else changes. So we focus on only one term, which like a generic x comma y data point, or the only data point in D. But if we had m data points, then there'll be an extra summation here. Okay. Now this is the partial derivative for the jth coordinate, and similarly partial derivative for the first coordinate will have an x1 here. The second coordinate will have x2 here. They are all getting multiplied with the same, you know, same term. Okay, this is just some number minus another number. Okay, right, for the generic data point. But if there is summation, there will be an extra, you know, whatever the final numbers are. Okay, so for each coordinate, there is going to be a partial derivative value which is going to constitute the gradient. Okay, so if theta is 4-dimensional, then there will be 4 such terms. Okay, now that vector, the gradient, is the same dimensionality as theta. So you just have to think in terms of doing vector sum or vector addition, or vector subtraction. Okay, so if you see this think of arranging theta 1, theta 2, theta 3, theta 4, you'll have the old thetas minus the gradient vector, if you think of the vector version of this. Okay, so it's like the old theta vector minus the gradient vector. Okay, so you're subtracting two vectors. So if you think of 2D plane, you have a vector, you have another vector, you subtract it from the previous one, then whatever the resultant vector is a new theta. So essentially, you have to think in terms of that what's happening in the 2D plane. It's just the gradient is nothing but a vector in that original plane. You're just the original theta is just getting perturbed to a new theta value. Okay. Okay. So just a aside that this particular expression, this update rule, as in this update rule, which is written here for the jth coordinate of the input. It's also called the Withdrawal learning rule. Okay. So it's basically focusing on a single training example and saying that if you have theta j, if you want to iterate on if you want to update the theta j, take one example, exactly the gradient that we derived earlier, right? This whole thing is the gradient of gradient of the loss, and then there's the alpha, which is learning rate. So if you just focus on one example in your training data and then update theta j, then that's a learning rule or an update rule. Learning and update rule is just word used to describe this update equation from going from old theta values, old theta j value to a new theta j value. You do this for all the coordinates. Okay. So what you observe here is that to update theta j, the only thing that is affecting is the jth entry of your feature. Okay, so the feature vector, ith feature vectors, jth entry is the one which is affecting the new theta. Okay, so that's also something special with the squared loss that we chose. Okay, which you can see it here also. This change only depends on the jth coordinate. Okay, of a generic example x. So this is a minor point, but okay, let's come back to this update rule. This is slightly different from the generic gradient descent update rule that we saw in the previous slide. The point is, at the high level, if the difference between h theta, okay, so at the current theta, if the difference between what h theta is predicting and y is small, okay, then the update is going to be small, right? Because this term is small, some small number times some feature value, but the small number times some alpha, as I said, think of it as 0.01 or something, which is called learning rate, but generally small number. So you won't be updating theta j much. But if h theta is very different from y, then you're going to have a large value here, right? And so theta will be updated, theta will change a lot. Okay, so it's just saying that if you're already at a good point, then your theta will not change too much. So there's just the intuition, trying to get some more intuition on this update rule, because that's the only secret sauce, or not secret sauce, but the key step in that for loop, which is the gradient descent algorithm or procedure, what are you going to call it? It's just a for loop where you're updating old theta to new theta, but the way you're updating it is adding or whatever, subtracting this gradient of the output with respect to the coordinates, okay, theta j coordinate, and you do that for all coordinates. So let's actually now put all of this together. Although we saw specific update rule in the previous slide, let's come back to our original objective. We wanted to find the best theta, right, for the linear model, assuming the squared loss cost function. So here is what is called the Manila gradient descent procedure, or you can also call it the batch gradient descent procedure. I think for simplicity, let's drop the word batch for now. Okay, it's just a gradient descent procedure. So what you've been given is the data set. It's fixed. Okay, the 100, let's say the 100 examples are fixed. You start with some random initial theta, and then you repeat. Per epoch just means there is some so per epoch just means per iteration. Okay, so this gradient descent iteration, just think of that iteration as an epoch. Okay, and in that per iteration of the gradient descent loop, you pick each coordinate. Okay, so if there are 4-dimensional theta, then you have a for loop saying that, hey, for each dimension, do an update. Okay, that update is, hey, the jth dimension, get a new value, which is the old value, minus learning rate, times the summation comes up because now the data set has m points, and this is exactly the gradient that we saw from before. Okay, the jth coordinate is only affected by xj. That's kind of the point we were making in the previous slide, but this is the gradient update step for the jth coordinate. You do it for all the 4 coordinates if you have four theta values to update, and then you repeat these epochs till convergence. Okay, till convergence just means as long as thetas are not too different from the previous thetas, the old thetas and the new thetas. Old thetas are on the right hand side or from the previous for loop execution, and new thetas are on the left hand side. Okay. So as long as the difference is small, like you can look at, hey, is the coordinate wise difference small for all coordinates, then you stop. Okay. Or you can also, instead of doing a repeat until convergence, you can also say, hey, I don't care about a while loop, let me just do a for loop. So you can say for, outer loop, for 1,000 rounds, just do this internal inside for loop. Is that clear? That's the gradient descent procedure, and you will be implementing it. So it's good to understand, the details now. Any questions here? Yeah.
What are the alternatives to gradient descent, and why is it most widely used?
So the question is, what are the alternatives to gradient descent and why is it most widely used? So there are several alternatives to search. So this is just a search problem. I told you the template of the function, and I told you the cost function. You just need to figure out how to get to a good candidate theta, which has the lowest cost value. That's a search problem, right? Broadly, there are many ways to do a search. Okay, do the search of finding the best theta. One approach is gradient descent. It belongs to the family of what are called first order methods. Okay, first order techniques depend on gradient information. So gradient descent is one, but there are many others which also depend on gradient information to get to the best theta. So that's the first order set of first order techniques. There are another set of methods which depend on second order information. Okay, these are, I guess, just called second order methods. And one example, so they use what is called the Jacobian. Okay, so they just use second derivatives but in addition to first derivative. So we are just using first derivative, the gradient. So you can use not Jacobian. They use the Hessian. Okay, so in case you have done linear algebra or calculus, you remember there's a notion called Hessian, or the second derivative. Okay, if you think of one dimension, there's a second partial derivative with respect to input, right? So you can use the Hessian information, and that is the second order method. So if you just think of, hey, what are the different approaches? There's one which is first order family, which includes gradient descent. There's one which is second order method, which includes I don't want to use the name, Newton's method, I think. So there are some second order methods. Okay, and there's also some methods which don't use either gradient information or second order, second derivative information. These are called zeroth order methods. Okay, so there are methods which kind of classified like this, and this is not the only classification. Okay, those are, I guess, called global optimization methods or zero order methods. Okay, so there are many methods to solve the search problem. If you let me just use zeroth order methods. They're not global optimization. Okay, so zeroth order, first order, second order is one way to say, hey, there's large buckets of methods within which first order has one set we are looking at, which is called gradient descent. Does it give you a sense of like how many? There are a lot of methods. Okay, and in particular, there's a class also which is being taught simultaneously on Thursdays, optimization, right? So you will be able to look at some of these methods if you want. So why is gradient descent popular? First of all, with second order and first order methods, the function has to be differentiable. In particular, for second order methods, you have to have second derivative. For first order methods, at least the function has to have first derivative. For zeroth order methods, we don't care. Okay, we don't care. We don't need the gradient, so we don't need the function to have derivative. Okay, that's a nice thing. But of course, so you can imagine if you are not using gradient information, it's challenging. Okay, you need more effort to find the best solution. Okay, if you have if you have more information like gradients or second order information, then you need less effort to find the best solution. Okay. So for so the popularity of gradient descent is because of the simplicity of this update, right? So you can see it's just take the previous parameter, subtract, a similar type of vector from that vector, right? So this template has been quite easy to implement, so that kind of lends to its popularity. It's also super popular for other differentiable functions, in particular deep learning methods, right? Not just this particular method, which is gradient descent, but you'll see another variant today called stochastic gradient descent. But in general, these first order methods are kind of easy to code up. Okay, and software supports automatically computing these gradients. Okay, you don't have to compute that the gradient of the loss, if I specify square loss, is exactly like this, and therefore I need to code up the update rule like this. That would be too much effort. Every time you change the loss function, you have to kind of change the gradient, and also it depends on H theta as well, right? So there's a software support via software that some of you might see in deep learning class, for example, PyTorch or TensorFlow. They let you compute the gradients of an output with respect to its input programmatically, okay, behind the scenes. So that makes it easy. Okay, so that's not very specific to machine learning. In general, those things were needed for partial differential equations and some other engineering areas. So that lends to the popularity of gradient methods. Okay. So it's easy to code up. I guess that's one way to say. Does anybody else have any inputs here? Yeah. What's it? Oh yeah, you can do 1 by m. Yeah, alpha upon m. Yeah, you can do that. Why is there no 1 by m? Because if m is 100, you just say, instead of alpha, you just use alpha prime, which is alpha by 100. So I agree. I mean, there's potentially needs to be 1 by m, for example. It's not that one is correct versus one is not. I mean, if there was a 1 divided by m, like let's say little m is 100, why is there no alpha by 100 here? Just think of alpha as again, scale it down by 100 and it will work. So yeah, I mean, here is just one template of an update rule. You can make it different. Like if you want to use 1 by m, you can. So I think in the loss function we did not use 1 by m, and so that's why it's not persistent here. We could use 1 by m in the loss function so that the loss function value is like an average of all these individual data point loss values rather than like a sum. Okay? If you wanted to normalize it that way, then it will appear here. Yeah, any other questions? Yeah. How do we find alpha value? That's a parameter of this procedure or a parameter of this algorithm. And so you can decide, so mathematicians or these folks have figured out what is the right way to choose this alpha as well as change it to ensure that you actually converge. Okay, as in like there is no way you cannot converge unless the objective function is non-convex. So the people have given some suggestions on how to choose alpha, but in practice, the first order rule of thumb or rule of thumb is basically pick an alpha such that you pick an alpha based on empirically seeing how your loss performs as a function of iteration. Okay. Yeah, you need to try out different values. Yeah. So intuition wise, if alpha is large, then you're gonna get away from the ball, right? So you can see that. So instead of going down, if alpha is large, what happens is your gradient step may make you jump up to this point, and then again your gradient step may jump up to that point. So you may actually like jump out of the ball. But if you take alpha to be small, really small, then you will be slowly moving rather than So alpha really determines how much of a jump you're making in this space. And so if you're making jumps, let's say from here to here, then that's going to translate to some jump in the loss vector, right? So alpha just determines how quickly you converge, but then a priori it is hard to figure out what is the best alpha. A priori I think it's hard to figure out, at least practice-wise. Theory-wise, people have suggestions. Yeah. You have some questions?
Yeah, I want to know what alpha is, but I want to just to start with the alpha value, so while we are coding, do we put alpha of something that we decide or
Yeah.
just,
Yeah.
we decide only like what alpha we want to start with?
Yes.
So normally like which value like 1, 2, 1.1.
Yes. So you chose something pretty arbitrary. So that's why maybe that his suggestion of scaling the gradient makes sense. Yeah, a priori it's very unclear. You can choose points. So very similar to regression. So the regularization coefficients, right? So where you have a search from 10 to the power minus 6 to 10 to the power maybe 3, like you increase up by a factor of 10. You can try alpha like that to get a sense of how does alpha influence my particular applied problem. I don't know if you have ever used regularization coefficient search with cross validation. I don't know, some of you have done 572. If you have done ridge regression, then there will be an L2 regularization term in addition to the loss function, and so there's a coefficient in front of it, and you'll say, hey, the coefficient strength should be 10 or 1 or 0.1 or 1 by 100. So you just search. Okay. This alpha is just a parameter of the algorithm, so you can get a sense of how are you converging based on this alpha, and it does influence. Okay, as I said in using illustration, it does influence. Yeah.
Alpha, I mean, not really, but it is inversely proportional to epoch. So if you have a very small learning rate, then you need more and more iterations to reach the conversion. And the other way around. If you're playing with different sets of variables.
Yes, but if you shoot up alpha too much, then you have an issue, which is what I said. Yeah.
Okay. In some sense, it is inversely proportional.
Yeah. So if you have really small alpha, then you need more epochs. Yes. Yeah. Yeah. Good point. Yeah. Somebody had a comment there. No. Here it's not fixed. I mean, at least in this pseudocode, it's not fixed because repeat until convergence, which we did not say what exactly is convergence, but it's exactly element wise, coordinate wise. Hey, theta new, theta old, is it like the difference is like 10 to the power minus 6 or something? Then stop. This is a while loop basically. If you had pre-decided, hey, for 1,000 iterations, just run this internal update, this update here for 1,000 iterations. After 1,000 iterations, you stop. And you can get a sense of whether you have conversion or not by looking at the loss value also. You can look at whether it's going down or not. Right? So as a function of iteration, or as a function of epoch, you can plot, hey, first epoch, this was the last value, second epoch is decreasing, third epoch is decreasing, and so on. So it should ideally decrease. Okay? You should go down the ball. For squared loss and linear loss functions, you should definitely go down the ball.
So we don't do, and basically we always follow while and when the function.
Oh, this n is determined. This n is also determined. This, if you want to convert this while loop to a for loop, then yeah, for loop you need to say how many steps you're doing. Right?
That was the thing that if the n is fixed, basically what
is fixed? This n.
Yeah, and
yeah, it is fixed because that's the dimensionality of your input.
Yeah, number of rows basically in my data set.
No, this n is not the number of rows. Sorry for the confusion. If anybody else has a confusion, this n is the number of coordinates of your theta. So think of n as 4 or 3. Let's say 4. This m is the number of data points.
Number of data points. Okay.
This m is the number of data points. And this outer loop is the number of iterations of your gradient descent. Okay. Don't get confused. Or spend a minute here. You'll be fine. Yeah.
So the final conversion, after the repeat for epoch.
Yeah. Until convergence. Yeah, but theta. So actually, the way this symbol might also, I didn't explain it earlier. The symbol is saying this is like a theta. You can write a superscript old here. You can write a superscript new here. So there's an old values at the beginning of this update, and there's some new values at the end of this update, right? So given the old values and given all this, you can get a new value, right? So once you evaluate theta j new, okay, for each of your, let's say, 4 coordinates, so you have theta j new, so you have theta new and a theta old. Why don't you just subtract them and take, like a norm difference, or even they do a squared loss if you want. So you have 2 vectors, do element-wise subtraction, and just square them and take a square root, for example. Just find the norm if you want.
So finally, the daylight function, the output would be in 4 dimensions, right? Not
Theta j is one coordinate of the 4-dimensional theta vector.
Yes. So
Yes.
it will be like four kind of.
Yeah, there will be 4 numbers. We try to search for 4 numbers, right? That's our problem.
That should be our local minima.
Yes, that theta ideally, hopefully, is our global minima if our function class is linear, which is the linear function, and have square law. Yeah.
That is when the loop ends. So that is the convergence, right?
Yeah, when that 4-dimensional vector is not changing much.
Okay.
Yeah, that 4-dimensional vector should not change much, and then you stop. You kind of, you're fine. Yeah. So I think you'll spend some time on this in the assignment too, which is going to come soon, and so you will have a little bit better sense of what's going on. Okay. And the reason why we are kind of working through this is because when you get to more and more complicated models, you will kind of lose touch with this, right? But you should know behind the scenes for the simplest model what's going on computationally, right? Otherwise, it's like building castles in the air, right? So, yeah.
When you combine, there is a chance that you do not correspond to the.
I am not combining them, right? This is like coordinate-wise update. I could have, instead of writing this for loop, I could have just written a vector update. Like I could have just written theta new is equal to theta old minus alpha times the gradient of the loss with respect to theta. I could have written that. So let me try. Let me use a different. So the gradient update I could have written as theta Okay, so this is a notation that you might see in books or maybe on blogs. So it's just saying this 4-dimension, this is 4-dimension minus alpha is like 0.01, let's say. This is the gradient of the loss with respect to theta. This is the 4-dimensional vector. The 4-dimensional vector, you're getting a 4-dimensional vector out. You just do a for loop on this, like say 1,000 times. That's the repeat thing over there. Actually, we can write that as well. Repeat until, right, theta new minus theta old is less than 10 to the power minus 6. So kind of keep doing this step again and again and again, where once you get theta new, that's going to be theta old for the next step. I didn't write it that way, but so you keep repeat this till the difference is like small. So this will, this is just a 2 norm. We'll kind of come back to this in a few slides. Okay. For those who have done linear algebra review, this should be kind of known. Okay, so it's a 2 norm. I mean, are people getting confused because I wrote this? This is the same as what we have in the slide here. So what I did is I dropped this for loop. This is for loop is per coordinate, but you can just vectorize it, right? So if you have four such equations, you can just say combine the 4 coordinates and call it theta new, combine the 4 coordinates, call it theta old, combine each of the gradients per coordinate, that's the partial derivative. For each per coordinate, you stack them together, that's the gradient. Okay. Yeah, for now, let's keep simple. So is this clear? This is a version of gradient descent. So as he asked Zoe, basically you can have all sorts of variations with whether this should be m here, whether should I do all m, whether I should have alpha something else. There are many bells and whistles that you can change. Okay, but this is intuitively this is one way to do the update. In fact, next couple of slides I talk about 2 variations. So let's see. Yeah. So let me just briefly mention what's so special about this batch gradient descent or the vanilla gradient descent. I prefer the word vanilla gradient descent. So one issue is that because we are looking at all examples, okay, to move one gradient update, right? It takes a lot of time. It's slow. So it's slow in the sense that the updates are more accurate in some sense, but it's unclear whether you need all the m data points to do one update every time. Okay, and that's what people have tried to kind of circumvent by coming up with a different algorithm or different slightly modified procedure. Okay, so these are now, they all belong to the family of first order methods. Okay, like so what we saw in the previous slide is called Manila gradient descent. What we are seeing in this slide is one description of what is called stochastic gradient descent. Okay, so what changed from previous slide to this slide is the summation term here. Okay, so in the previous slide, every epoch we were doing the gradient was computed with respect to all the data points, all my data points. Okay, all 100 data points, for example. What changed is here we are doing something similar, but there's an extra for loop. Okay, so the 100 data points are now not immediately, all are not being considered together. Okay, now it seems like a subtle change, but it does change the update. Okay, these updates are not going to be the same as the original update because the summation went out. Okay, so that's something we can discuss in a second. Yes, there's a question. M is the number of data points. Rows, yes. Yes, M is the number of rows. Yeah. If you think of a tabular data set, M is the number of rows. Now, why is, yeah. Theta values for every, yeah, we are kind of updating old to new for every, I mean, we'll pick one data point, go from old to new, and now we'll have that new to be the new, or like the next time we'll use a different data point to update from old to new and so on. So we are kind of going from old to new, but you're using only one data point, one data point per each of these updates. Okay, so that's different from saying, hey, use all the data points to go from old to new in one step. And that's because if you use only one data point, the gradient is going to look different, right? So the gradient is different. So the new is going to be different. Okay, so that's the key difference between stochastic gradient descent and vanilla gradient descent. Okay, it's not exactly stochastic here. This word stochastic, by the way, the word just means random. So whenever people say stochastic, they just mean random. Okay, this is exactly synonymous. So instead of this for loop here, what you could do is like randomly pick a data point. Okay, here instead of doing this for loop, you say, hey, every time randomly pick a data point, do the update. Randomly pick a data point, do an update. Randomly pick a data point, do an update. Okay, instead of linearly, hey, take the first data point, do an update. Take the second data point, do an update. Take the third data point, do an update. Instead of that, you could randomly pick. Okay, so that's, I guess, the original reason why it's called stochastic gradient descent. Computation time, whether we do, so it's a randomized basis? Instead of this for loop, I said random. Yeah. No, if you take random m times, and as long as calling the random function is constant, I mean, if you do m times and here you're doing m times, there's no computation difference, right? Yeah, but there is a difference between doing this and doing what we saw in the previous slide, because that has a summation m here, and so one may do better than the other, in the sense that you may get so this, for example, each update requires much lesser computation. You just pick a random point, and for that, finding the gradient is kind of easier than finding the gradient for all the points and then summing up together. Okay? But the update, that update could lead to a better convergence than this update, or this could lead to a better convergence than that update. That a priori we cannot say, okay, without at least at our level of discussion. So, any other question? Okay. Yeah. So the big change that happened is now we're not taking the gradient of the full loss. So remember, the original loss had a summation here. The gradient of the loss was supposed to have a summation here. We're not taking the gradient of the loss actually. We're taking some other proxy. Okay. The proxy is just, hey, gradient of one data point instead of the gradient of the whole loss function, just a gradient of one data point. So that's why the second bullet point says, the update is going to be in some sense noisy because it doesn't reflect the actual gradient of the loss with respect to parameter. Okay. But apparently empirically people have found out it helps with finding a theta that does generalize better. Okay, we'll talk about what is generalization later, but it has some nice properties for translating, finding a good model. Okay, which is not specified in the loss function only. So this is like goodness of the model is specified by the loss function. Here, the recent research has shown that the algorithm also influences what model you get, and so whether it's good or not in terms of test error or whatever generalization error. Okay, but that's a point that is not important at this point. Any questions for this? At least, so what we want to find out at least these two algorithms is just the difference between them. Okay, there's some trade-off between the update rule of the previous one and the update rule of the current one. Okay, so let's actually step back, ask a couple of quick questions. So one is, does initialization matter? So what do you guys think? Does initialization matter? Everything else is the same except initialization. Yeah, so that's a good answer. So basically for convex functions, it kind of doesn't matter. Okay. Of course, if you're initializing like much far away, maybe you need more iterations, but then kind of nothing much changes in the nature of the problem. Okay. So second thing is, so for us actually J of theta is actually convex. For us means for linear model specification and for squared loss, J theta is convex. Okay, that's a fact for now. We'll not kind of supporting evidence of why it is convex, but it is convex. In fact, it looks like the ball illustration that we've been seeing. That's exactly how it looks like. If you remember, like y is equal to x squared, actually y is equal to minus x squared, let's say. It's exactly, y is equal to x squared looks like a parabola, right? Inverted parabola, right? So that's exactly what's going on with the loss function. So it exactly looks like a ball. So it is convex. Okay? Now the question is, do we have to? So we presented gradient descent approach. Okay, that's a numerical approach. It's actually doing iteratively, like getting some new and better, hopefully candidate parameters, and hopefully getting to the best model, best according to the training data. And then we can do some, once we get to the best model, we can think of, hey, how does it perform on a test set or a validation set, whatever. That's for later. The question is, can we actually do something different than a numerical algorithm? Okay, so or this the gradient descent approach that we saw. Okay, so we'll try to approach computing the best model from a slightly different perspective now. Okay, so the different perspective is using system of equations idea. Okay, basically linear algebra. So it's again give you a gist of how working with matrices and vectors can manifest in different ways, right? So let's start with a basic setting. So if we have let's say this is really we're stepping away from machine learning for a second and our search for theta for a second. We just want to say, hey, if we have three unknowns x, y, and z, how many equations do we need to identify those unknowns? Okay, so this is just a how many equations. So how many equations do we need to identify the values of three unknowns like x, y, and z? Where x, y, and z are just think of them scalar unknown values. Scalar just means one value or one one dimensional. Three, right? So what if we have less equations than unknowns? Right? It's called an underdetermined system. And if you have more equations than unknowns, it's called an overdetermined system. Okay, so underdetermined and overdetermined just means the number of equations that we have versus the number of unknowns that we want to find. Okay, this is again a search problem. Okay, it's stated in a different way, but we want to search for the values x, y, and z for given equations for them, but not the values themselves. So what is the case for our setting? Okay? And now how do we connect this to our setting is because we are fundamentally our model specification is actually a linear function. Okay, so on training data, it turns out that we'll get actually a linear equation. Okay? And so what do I mean by that? We'll clarify in a couple of slides, but let's come back to what we've seen so far. Like if you have lots of features, and this is just a recap on what we saw with KNN and decision trees. If you have lots of features, then may not be a good idea to use decision trees because like too many splits or too many split choices. Okay, if you have lots of rows, then KNN is not a good fit because it's lazy, and so every time you make a query, if you have a billion rows, it has to scan through the billion entries essentially and find the distances to find the neighbors or whatever, compute similarities to find the nearest neighbors and then make an estimate. So these are the trade-offs for those two methods that we've seen. Now, if we kind of think of the tabular structure we've been so far, like when we have all our data points one below the other, so x1, x2, x3, x100, the input matrix. So the input matrix is matrix because I'm now arranging each data point as a row of a matrix. Okay, it can be a tall matrix or it can be a wide matrix. Okay, so if it's a tall matrix, then the number of rows is much greater than the number of columns. Okay, now you can make this. Now you can try to make a connection to overdetermined systems. Okay, as a teaser for now. Now, if the matrix is wide, it means that the number of rows is much smaller, or this just means much smaller, but as long as it's smaller, it's fine. So if m is less than n, okay, which is it's a wide matrix, then we are in an underdetermined situation. Okay, so we are overdetermined or underdetermined depending on the number of rows that we have in the data set compared to the number of coefficients or number of features that we have. Okay. So we're going to now look at a matrix way of solving to the best theta. Same loss criteria as before. Okay. So x is our input matrix now. So again, x is a matrix that belongs to the set of all matrices. This is the short form for set of all matrices. Just I wanted to explain because you may see it a couple of times. Just a set of matrices which has m cross n cells, and each cell has a real number in it. Okay, that's what it means. And y now, okay, it's different. So this y now is a vector. Okay, it's a vector in m dimensions. Okay, so y is a vector which is 100 coordinates. Why 100? Because we have 100 data points in our running example. Okay. Then our goal is our goal, which although we wrote it in a using a loss function way, a different way we can write, different way to say, hey, we want to fit our model, find the theta such that our H theta predicts well on the training data, is to say we want to find theta such that x theta is equal to y. So instead of talking about a loss function, I'm saying that, hey, I want to find a theta. Given a theta, such a theta produces outputs. Those outputs should be as close to the training data's real outputs, right? Training data. So let's say if you take the first example, H theta of the first example should be close to the y of first example, right? That in a vector form is just this system of equations. Vector form just means the first row should be the same as the first output, second row should be the same as second output, and so on. There are m equations here. M is the number of rows, okay? And so this is actually our goal. Okay? This is what we wanted to find a theta such that this is true. Okay. Now you may say, hey, how can a priori I can say that this can be true because the system could be underdetermined or overdetermined, and depending on that, I may not have a solution. Sorry, I may have too many solutions, or I may not have any solution, Only when m is equal to n, maybe I can say, hey, I can get a theta which actually satisfies this. That was there was a basic illustration slide before. Yeah. Sorry, can you repeat? So theta is a vector which is, let's say, 4 dimensions. X is a matrix which is 100 cross 4. Okay. Theta is a vector which is 4 dimensions, and then you have on output which is 100 coordinate vector. That should be the same as the 100 coordinate vector that you have in your training data. So theta is just a 4-dimensional vector that you want, such that this is true. So theta is the unknown. You have a system of equations. When I already said m is equal to 100 and theta is 4-dimensional, it's already overdetermined, but it's just a system of equations where theta is unknown, x is given, y is given. You want theta to satisfy this equation. Yeah, 100 cross 4. Yeah. Theta is a 4 cross 1. It's a vector. Yeah, unknown. Yeah. Any confusion here? See, people are exhausted, but let's spend some more time. A few more minutes. Yeah. So, a couple of quick comments was that, hey, we are kind of folding in that last coordinate. So remember, I think earlier when we defined the inner product, we said, hey, there's a theta naught which is the bias or the intercept. We just said the first, one of the features could be 1 with a value of 1, so that I can just merge them together. So let's actually ignore that part. Okay, so in the sense that either you can talk about n plus 1 or you can talk about n, but at the end of the day, you have a system of equations, okay, like this. Okay, so so first of all, if m is 100 and theta is 4 dimension, I cannot find a theta such that that system of equation actually holds exactly. I mean, very hard, right? You have too many equations, and how can the same theta satisfy all these? Maybe if there are only 4 equations, maybe 4 equations, 4 unknowns, you would get probably unique solutions. But if you have many equations, sometimes theta will not satisfy. Right? Some equations theta will not satisfy. So for that, we can talk about a residual vector. Okay, this vector again is going to be 100 dimensional. Okay, because we have 100 observations. Okay, the residual vector is just y minus x theta. Okay, just y is a vector, 100 dimensional vector, x theta is a x times theta is a 100 dimensional vector. Subtract them element wise, you get a residual vector. Okay. Now, least squares criteria says that says how to find the theta, how to find a theta. Okay, so you find a theta which minimizes this residual vector. Okay, so this residual vector R, this 2 vertical lines, subscript 2, superscript 2. This is a shorthand. Okay, to say what? To say, hey, this residual vector, take each coordinate, square it, sum them. Okay, and that's it. That's what this 2 norm square means. Okay, it's just the if we have a vector, each coordinate, square them, and then sum it. Okay. If there was not a 2 norm square, so this is a 2 norm square because it's a subscript of 2. That's why it's called 2 norm square, because it's the usual square operation. If it was just 2 norm, then you would just do element by square, sum them, and take a square root. Okay, that's a 2 norm. So the criteria that we saw in the first part where we're doing gradient descent, it can be written in terms of doing something with this residual. Okay, it can be written in terms of find theta such that this residual is the smallest in terms of 2 norm square. Okay. So R depends on theta. So if you change the theta, residuals change, then this value changes. In fact, this value here is exactly the loss criteria that we saw in the first part. Okay. So now let's now talk about linear algebra. Okay, which is how to find this theta. Okay, so we know we want to find a theta that minimizes this residual. Okay, and we can actually find it analytically. So analytically just means not using. So we talked about the gradient descent method before. It was just telling a computation procedure. Hey, repeat this procedure for 1,000 iterations or 1,000 epochs, and you will get a theta which minimizes the loss function. It was a prescription, but it didn't tell you theta directly in terms of the data set. Okay, just so happens for linear models and the squared laws that we use, we can actually directly write, hey, here's a theta solution, which is this exact function of the data. Okay, you don't have to do that iteration. Okay, and some of you might have seen this function before. So analytical solution just means writing theta, okay, finding a theta and writing it as an explicit function of the data set. Okay, that's all it means. Okay, analytical just means a formula. Analytical solution just means give me a formula for theta. Don't tell me to do gradient descent. You know, that's the kind of idea here. And the solution here is the candidate solution. It just says, hey, if you want to find theta, find a theta such that find a theta that makes this residual vector. Remember this vector here. This residual vector is perpendicular. It's perpendicular to every vector in the range space of X. Okay. Now there's some words there. So the range space of X is given as little bracket here. Okay. The range space of X is saying, hey, you have this matrix, multiply with every vector that is possible. Like every vector, hit it on the right hand side, you get some vector as the output. Select all those vectors, whatever vectors are output. That's called the range space of that matrix X. Because these, changing, you keep on inputting Z for every, pick the X, you'll get many vectors, collect them all together. That's called the range space. Okay. Now, the analytical solution they are just saying is that, hey, you have all these vectors which correspond to the range space. As long as you can find a theta that makes the residual perpendicular to this range space, you're done. Okay, so that's the candidate solution that the slide is saying. That's the candidate solution. Why is that a candidate solution? We will see soon. But let's actually spend some time on this figure here. So because we'll see a couple of these figures, the same figure in the next couple of slides. Think of range space as like this plane. Okay. Range space is just it's a vector space. Okay, it says range space. It's a vector space which is just called the range space for some reason. And the reason is because that vector space is formed by taking vectors from Rn and just multiplying it with a fixed X matrix. Okay, the data matrix, the feature matrix, basically. Okay. So all we're saying is, if let's say if residuals are 0. Okay, so if this gray area is the range space, if y belongs to that range space, then you actually know that there is a theta for which x theta is equal to y. Okay. Because remember, this range space is all vectors that can be produced by hitting some vectors to x. Okay. If y also belongs to this range space, then you can actually find a theta for which x theta is equal to y. But y generally will not belong to the range space. Y will be somewhere outside. Okay. And that's why you can't just solve the system of equations because it's overdetermined. Y will be outside. So all we're saying is the best theta is actually the theta for which, if you project y to this range space, okay, perpendicularly, that's going to be a vector, okay, some vector here in the range space. The theta corresponding to that vector is the best theta. Okay. So there is a y outside this range space, project it down perpendicularly. There is some vector here. Okay, that vector should be the output of your theta that you want. So this vector here is the residual vector because it's y minus, so it's like y vector minus x theta vector. This is the residual vector. That vector is perpendicular to any vector in that vector space. Okay. So that's what we want to find, and that's the suggestion that this is what we want to do, okay, to find the best theta. I mean, to find the best theta in this way. So yeah, find the best theta such that this is as close to y as possible. If you wanted to do this, if y already was in the range space, we are already done. There is some theta for which x theta is equal to y. So you can just solve the system of equations, you get theta. But y may not be in that range space, and so we have to do something. So we have to find a theta, and they're saying, hey, the theta that minimizes this residual vector in terms of the 2 norm square is exactly that theta for which this residual is perpendicular to the range space. Okay, there is no other. If the residual is not perpendicular, then that's not the best theta. That minimizes the residual. Okay. So actually, what we'll do is, because we're running out of time, we'll stop here. We'll stop here and resume next class. So I'll give you a sense of, like, we're getting lost in some details, right? Like in each I guess a few minutes. But there's the broader context. What did we try to do today? Is stick with a simple model, which is a linear model. That was the specification of model class. Then we try to motivate ourselves in terms of, like, defining how to say quantitatively a model is good or not. That's why we defined the loss function, the cost criteria. Then we spent a lot of time on trying to figure out how to find the best model given the loss criteria and the model specification. That we did using the general template of gradient descent. That is not specific to linear models. Okay, you can use that gradient descent idea for many other types of models, including deep learning models. Later on, if we have time, we can talk about it. So we saw a couple. We saw regular gradient descent, Manila gradient descent, or batch gradient descent, and we also saw stochastic gradient. There's a slight variation between them, but there were some trade-offs. We discussed that. Now what we're trying to do is, hey, the linear model is so simple, and we know that the cost function is like a parabola. Is there a different approach to find the best model? In fact, there's an analytical approach. There's a closed form expression. There's a formula which relates theta, the best theta, to the data set. Okay, and so we're trying to inch towards that. And to do that, we're getting a geometric picture of what's going on. So starting from the system of equations, idea. Okay. So next time we'll try to kind of finish this up. Okay. Using normal equations and so on. So that's where we are. So we want to kind of finish up the story of linear models and say, hey, linear models can be solved using gradient descent, but they can also be solved using, actually without doing iterative procedures, without doing computational procedures, using system of equations ideas, okay, using matrix algebra. That's the intention. Okay, so I'll see you guys next time.